Hello and welcome to this session. In this session, we'll start with the numerical. We studied the open circuit test and the short circuit test after deriving the approximate equivalent circuit of a transformer. We studied the open circuit and short circuit test of a transformer. Using that knowledge about open circuit test and short circuit test, we'll be doing them on numerical. So this is the numerical that we will be doing. So the question here is equivalent circuit impedance of a 20 kVA. So equivalent circuit impedance of a 20 kVA, 8000 by 240 volts. 60 transformer are to be determined using and the open circuit test and the short circuit test on the transformer have already been performed, and these were the readings. The open circuit test, the rated voltage was 8000 volts. The current flowing at the time of in the open circuit test is 0.214 amperes, and power is 400 watts. And short circuit test, we have Vs equal to 489 volts. So you can see it's much less as compared to VOC, less, almost 18 times less. ISC is equal to 2.5 amperes and PSC is equal to 240 watts. Find the impedance of the approximate equivalent circuit. Refer to the primary side, and we have to also sketch this. So we have already seen in case of the open circuit test and the short circuit test, what we do is we can determine YOC from the magnitude of YOC and knowing the angle theta. Fine. Where YOC is equal to what? It is equal to IOC divided by VOC, and angle theta is actually what? It is cos inverse of VOC divided by VOC IOC. So IOC is given to us, it is 0.214 amperes, VOC is 8000 volts, and angle cos inverse of VOC is 400 watts, VOC is 8000 into 0.214. So if you calculate this comes out to be equal to 0.0000268 angle minus 76.5 degrees. Fine. That this is actually equal to what? This is GC minus JBM. Fine. So if we put this in Cartesian form from this polar coordinates, we can see this is 0.000268 cos of minus 76.5 degrees plus 0.000268 sine of minus 76.5 degrees. So that is equal to this comes out to be equal to 0.00063. It's 5 zeros minus J 0.0000261. These are 4 zeros. These are 5 zeros here, 4 zeros here. So GC equal to 0.0000063 and BM is equal to 0.0000261 minus actually rather. So that means therefore RC is equal to 1 by GC. So that is 1 by 0.0000063, 1 by 0.0000063. That means it is equal to 159 kilo ohms. Fine. So you can see RC is a very large resistance. So naturally, if the voltage is 8000 volts, the excitation current, the current flowing through this branch will be very less. And XM, that is the magnetization branch, is equal to 1 divided by BM, that's 1 divided by 0.000261, that is equal to 38.4 kilo ohms. So we have found out RC and XM from the knowledge of open circuit test. Now using the analyzing the short circuit test, what we have from the short circuit test, we can say ZSC is equal to ZSC angle theta, uh, where ZSC is given by uh, VSC divided by ISC angle cos inverse of PSC divided by VSC into ISC. So VSC here is what VSC has been given to us. It is equal to 489 volts. ISC is equal to 2.5 amperes, and angle cos inverse of PSC divided by VSC, that is cos inverse of PSC is 240 watts divided by 489 into 2.5. So solving this, you'll get ZSC. This comes out to be equal to 195.6 angle 78.7 degrees. That is in Cartesian form equal to 38.4 plus J 192 ohms. So your this is what? This is actually R equivalent plus J X equivalent. So you can see R equivalent, that's actually RP plus A square RS is equal to 38.4 ohms only. So as compared to RC, which is 159 kilo ohms, RP and RS, they are very less in magnitude, and they have to be very less in magnitude because we do not want the copper loss to be very high. We do not want I square R to be very high. So naturally, the resistance of the primary windings and the secondary windings is relatively less. And so this is your R equivalent is therefore 38.4 and X equivalent is equal to 192 ohms. So using these two, now we have actually found out RC and XM, we have found out R equivalent and X equivalent. So if we do not know the turns ratio in this case, so we cannot actually comment upon that, but we can find out the approximate equivalent circuit of this transformer, and this here represents the approximate equivalent circuit of this transformer. So in addition to this, I'll be forwarding another video that actually demonstrates how to perform an open circuit test and a short circuit test in case of a transformer. So that will be all for this session. In the next session, we'll be starting with the per unit impedance. In the per units, we'll be actually doing first the per unit measurements in case of transformers, how we can apply that to transformers.